Thank you for the coming. And thank you for the possibility to be here. So this is a joint talk with my co-authors from the University of Wurzburg and the University of Coimbra. And so let me start to reminding what is the Stiefel manifold. This is just a set of k-orthogonal linearly independent vectors in n-dimensional vector space endowed with some scalar product. Yeah, yeah. We are mostly will be interested. I don't know. Doesn't has the red spot. We mostly will be interested in this talk working with the vector subspaces in Rn. So the first time this kind of structure was introduced by the Stiefel in his thesis, wrote under the supervising of Hopf in the Zurich, in ETH. Yeah, and he was talking about these direction fields in teleparallelism in the n-dimensional vector manifolds. Okay, so this is just publicity, propaganda slide. So if you Google Stiefel manifold, then you can find thousands of applications and so on. So this is just a copy-paste. Okay, let me give a couple of the realizations, 2, 3 actually mentioned how it can be described, Stiefel manifolds, and what we wanted in our work. So one of the way to look on the Stiefel manifold is just look on k-orthonormal frames in Rn. Yeah, so we consider that can be written as a matrices, rectangular matrices n times k, and such that xt by transposed by x is equal to the identity, and it can be seen, Stiefel manifold can be seen as an embedded manifold to the space of these rectangular matrices, and then one can calculate. So I need something like to show this. Let me use the old style red spot. So this is just a tangent space at point x. You fix x and you calculate the tangent space, and the tangent space can be described by all rectangular matrices such that the product x transposed by z is q-symmetric matrix. Matrix belongs to the SOK. Yeah, but from other side, somehow my collaborators, they were working with engineers, and therefore they asked some formulas and so on. So we produced, so anyone can produce this projection. So you take whatever rectangular matrices and you can calculate what is the tangent vector if you project from the this vector space to the tangent space at the Stiefel manifold. Okay, yes. Yeah, and it also can be looked at the pre-image of that kind of map. You take map from the rectangular matrices to the space of symmetric matrices, and if you take the pre-image of the identity, you get the Stiefel manifold. And then you can consider this, under this embedding, you can consider the Stiefel manifold as a Riemannian manifold. As a Riemannian manifold under this trace matrix. So you take whatever rectangular matrices, you calculate this trace matrix, and this trace matrix give us the Riemannian metric on the Stiefel manifold. So from that moment, we can consider the Stiefel manifold as a Riemannian one. Another way to look on the Stiefel manifold is to look at this like on the homogeneous space. So we start from the orthogonal matrices, n by n, and we define this left action. It's just multiplying the point x from the Stiefel manifold by the rectangular matrix x n by n. And then one look for the isotropy. So fix any point x and look for the isotropy subgroup. So those elements in the Stiefel manifold that stable under the action. And then quotient the orthogonal group by this subgroup. This subgroup isomorphic to the orthogonal matrices n minus k order. So this is one way that in the literature usually used to to consider the Stiefel manifold as the homogeneous one. And there is another way. You just change the group. In this case, the group is the direct product of of orthogonal matrices n by n with OK, and this is the action. Yeah, so you take two matrices and you multiply them by this way. So actually, this comes from this idea comes from the action that can produce by invariant action group ON cross ON on group ON on itself. But anyway, so under this action also one can find the isotropy subgroup, and then when we quotient it for any x from the Stiefel, and this isotropy group has this kind of is isomorphic to this product of the orthogonal group. So this is another way to look on the Stiefel manifold as the homogeneous space as that is diffeomorphic to the quotient of groups. And so we already mentioned that under the embedding into the rectangular matrices, the Stiefel manifold is a Riemannian manifold. For the homogeneous manifolds, we also can introduce the metric. Yes, so in this case, we just take the standard metric for the skew-symmetric matrices, and then under the group action, we defined the left invariant metric on the group, and then it's come to the Stiefel manifold. I'm sorry, this is one more. Yes, but so this is a different approaches to look on the Stiefel manifold as a Riemannian manifold, and in different literature, people were using different realizations, and they were solving some variational problem, looking for geodesics and so on, and then it was it is a mess in the literature, different realization, different geodesics, different approaches, and so on and so on. So the idea, and when we started to discuss it, we decided to describe all these cases as one case with metric that live in one parametric family. Essentially what we did. So if we look on this group, yes, and the corresponding Lie algebra, SON, SOK, then we take the trace metric for SON and trace metric for SOK and take the linear combination of them. Then, of course, you can divide by one of the parameters, real parameters that is not zero, and you come to that expression. Yeah. So we decided to work with this one parametric family, and for different parameters, what is interesting that this kind of metric for different parameters alpha recover all these previous considerations. Yeah, but then, so there is a unified method of calculation, geodesics, Riemannian geodesics in this case, and so on. So, yeah, so we define this alpha, one defined this alpha metric on the Lie algebra, and then use the left translation, we actually get bi-invariant metric on the pseudo-Riemannian, on the group, and this metric will be pseudo-Riemannian. Yes, it's pseudo-Riemannian in the sense that it's not positive definite, but it is not positive definite. Yes, and so this is our action. So the first two lines is just reminding what's happened. And then, of course, since we have this projection from the group to the quotient group, then we have this submersion, but we would like to work with Riemannian submersion or pseudo-Riemannian submersion, if you want. So for that, we need just adjust correctly the metric. Yeah. So okay, under this submersion, of course, we have the projection, and then when we calculate the differential, for example, at the identity, then this differential will have, of course, the kernel. So by the way, here you see how to calculate the projection from the Lie algebra to the tangent space at point x. So this is just a differentiation, nothing more than just a differentiation of the action in this case. But as I told, we want to have something like Riemannian subnotion. Riemannian subnotion. Okay, what is this written? This is the kernel, and the kernel will be called vertical space. Yes, vertical space. And this is described, of course, like in this way. And since we have this alpha metric on that Lie algebra, yes, then for that V space in the Lie algebra, of course, we can define the orthogonal complement. And the orthogonal complement, yeah, so we have this kind of two vector spaces that they are orthogonal, and they are well defined if and only if the metric is not, this indefinite scalar product is not degenerate. So then this is a true orthogonal complement, and this happened if alpha is not equal to -1. So we will see how this -1 appear later. So under this condition, we defined, and what are the properties? So if we fix X, and then we look on the algebraic properties of the vertical space and the orthogonal complement, they possess this type Cartan decomposition. So the T, the vertical space is actually the Lie algebra. It's closed under the Lie brackets of the vector fields or vectors. Then it is reductive in a sense that it's a joint invariant under the action of P. And the third property, when the commutator contains the commutator of P, that orthogonal complement to the kernel, so the kernel is contained in the commutator space or commutator ideal. This will be useful for us when we start to look for the geodesics on the Stiefel, and it will be related to the specific distribution on this group SON, SOK. Okay, so this is reflect in terms of the distribution. If we defined later from P, we use the left translation, and we define the distribution on the group, yes? So there are names, the kernel, the left translation of the kernel define the vertical distribution, and the orthogonal complement, left translation of orthogonal complement define the horizontal distribution. And this is just, in other words, complete non-integrability or non-integrability of this left invariant distribution, or the bracket generating property depends on the people, on the science. I will come to that later. But anyway, so this is something concrete, just example. So what happened if X has this very simple form? It's just K by K identity matrix, and then it is 0. Then if we write the matrices, Q-symmetric matrices in this block diagonal form, so omega is from SON, but we write it in this diagonal form, SOK block, then SON minus K block, and the complementary part B size is from SOK. Then the vertical and the horizontal projection with respect of that metric orthogonal decomposition into the vertical part and the horizontal part look like this one. And you see that we have dividing by alpha plus 1 that says you that alpha is equal to -1 is a bad number. And this is exactly why when the case when the metric, this alpha metric is degenerate. Okay, great. Now, yes, okay. Nice commutative diagrams. So the G in our, from that moment, if I do not say something else, G is this SON cross SOK group acting on the Stiefel manifold, and then the left action on the group produce the motion, yes, motion on the Stiefel manifold at the level of the different linear maps. So the identity group has the decomposition of the Lie algebra into the P and K space. And the identity it projects to the stable point, stabilizing point. And if the left action differential of the left action give us the distributions, so G, H at any point G, it's a horizontal distribution on the group. V is the vertical, that is the left translation of the kernel. And okay, under this action, we come to the motion from the fixed stable point to any other point on the Stiefel manifold. Okay, this is standard way to see that one. And yes, now what, but what we want that the metric, so we have alpha metric that is defined on G, and it can be projected in P, and then under the left translation, it's defined metric on H, on the distribution H, and in this case, it's called sub-Riemannian metric. Okay, pseudo-Riemannian. Sub, because it is defined on the on the distribution only, and Riemannian or semi-Riemannian, this depends on the says about indices. But what we want, since here there is the isomorphism between at each point G and the point on the Stiefel manifold, isomorphism between this vector space and the tangent space to the C. Yes. No. It's interesting, but okay, I will show you some more concrete examples. So, and the idea is that the restriction of the metric, this bi-invariant metric on the tangent space of G, or the restriction to H, will give us Riemannian metric on the tangent space to the tangent space to the Stiefel. And then we can use this Riemannian metric on the Stiefel, Riemannian or pseudo-Riemannian. Yeah? Okay, this is just a calculation how this alpha metric will look like on the Stiefel manifold at each, where X is this fixed isotropy point, and Xi1, Xi2 is just two tangent vectors in this form. But what one want to relate, that this metric, okay, that terrible formula, I didn't repeat it, but anyway. So that terrible formula is exactly coincide with the projection of the alpha metric on the horizontal space. Yes, in this case, if we have this kind of relation, then the submersion became Riemannian submersion or pseudo-Riemannian submersion. Pseudo-Riemannian submersion. Okay, here just a formula how the Xi tangent vector to the Stiefel manifold is related to the projection of skew-symmetric matrix to the horizontal part. Yes, to the horizontal part. I didn't write the vertical, but for vertical, it's also possible to write such kind of things. Okay, now, how, for what parameter alpha the metric is related to the known in the literature. So if alpha is equal to 1, okay, the metric on the Stiefel manifold look like this one, and I give this relation only, and how look like the horizontal and vertical distribution only for that specific point, most simple when the calculations are not so, formulas are nicer. Yes, so if alpha is equal to 1, then this metric was considered in these papers, and in this case, okay, the metric is given, and the vertical and horizontal distributions, they are given by this kind of decomposition. So if we have, I remind you that A, B, and C, they were, yeah, here. If we write the elements from the Lie algebra in this form, then the elements of the horizontal of that complement to the kernel look like this one, and this define the left invariant translation. Yeah, so that was used in this case. For alpha is equal minus 1/2, you see, this is, so for alpha is equal to 1, it was Riemannian metric. For alpha is equal to minus 1/2, it's also Riemannian when we restrict it to the Stiefel manifold, and this metric is up to coefficient 2 is just the metric inherited from the embedding into the rectangular matrices. So, in spite that it was defined through the action of that group, if alpha is equal to that parameter, then the metric, this bi-invariant metric on the horizontal distribution is actually coincide with, and define the metric on the Stiefel manifold coincide with the embedding metric. So it was used, for example, in these papers. Then for alpha is equal to the infinity, alpha is equal to the infinity was used. Of course, it was not used like alpha is equal to the minus infinity, but we can recover the metric is used in that papers where people were, this is more applied paper, for example, when they tried to mimic the Castasio algorithm, so producing the spline, for example, cubic spline on the Stiefel manifold. And they tried to connect 2 points by the geodesic on the Stiefel manifold. They didn't succeed to do this, and they changed the connection between the 2 points on the Stiefel manifold by the curve of constant geodesic curvature, not zero curvature, but the constant geodesic curvature. And that was pretty much just by calculation. When I was trying to talk to that people and ask how you come to this kind of calculations, just trying, failing, trying, and so on. But here now it will be in the general framework, and that's why I'm somehow like it. Now alpha is equal to 0. Now, if alpha is equal to 0, then it's not clear how to interpret it. Yes, but there is this way. So this is the first line is written at the level of the Lie algebra. But if we write it formally, since we have formula for any tangent vector on the Stiefel manifold, we come to that one formula. And here to take alpha to the 0 is not a problem. It's not a problem. So it should be some interpretation at the level of the Lie algebras too. Yes, and if we look on how look like the horizontal distribution in this case, so it depends on alpha. And if alpha go to 0, we also has a rather nice interpretation and so on. So what's happened? Actually, this is everything depends how you write the projection. So the projection is written in this way, and if we divide by 1 over alpha, then it is, and alpha go to the 0, then we have very nice limit that is just this limit on the tangent space, And therefore, we can take this expression and put it there in the matrix, yes? So it's just using the linearity of the trace, and we see that since this has nice limits, so alpha multiplied by trace of some finite number, let's go to the alpha. So the trace metric is actually when alpha go to 0, it's go to that one. Okay, now if we look on what's happened with the distribution, with the horizontal distribution in this case, then the vertical part for that alpha is equal to 0. Taking the limit, we have this vertical, we have this horizontal. And if we now apply the property that these V and H for any psi and A and B, they have to be orthogonal, we actually get to the position that A is equal to psi. So this is just 0. And we see that yes, probably this is on the next slide. Yes, and then we see that the horizontal distribution is defined by this one and the vertical one by this diagonal one. And this is completely coincide with the case when we have only one group acting, ON. OK disappears. So again, for alpha is equal to 0, we recover another representation of the Stiefel manifold as a Riemannian manifold coming from the action of the just one group ON. So, great. And that is a reference where, okay, for example, there are a lot of references where this kind of representation of the Stiefel manifold used. Yes. Yep. And then, yeah, since people in the engineering, somehow they were busy with producing some Riemannian geodesics or writing the Euler-Langrange equation, we decided to write one that, okay, the family of these equations, Euler-Langrange equations, that depends on the parameter alpha. Since we know now that for different alpha, we have different realizations, so we decided to do this. So, and then it's just a question of minimizing of the functional, yeah, from this space of rectangular matrices and space of symmetric matrices, this functional, where this S is just symmetric matrix, so it serves like Lagrange multiplier at the level of the variational problems Lagrange calculation, writing these equations. Okay, this look like a little bit longer. The first line is, so finally everything reduced to this initial value problem where we have the second order equation, first line, second order equation. The second line is just says that we have to work. So this is second order equation in the space of rectangular matrices. The second equation says us that we have to be on the Stiefel manifold. X transposed X has to be is identity, and the last two lines is just initial point and initial velocity vector. But what is interesting that expression somehow can be thought like invariant on T. So X is just a tangent vector at any point when curve moves on the Stiefel manifold, but this is somehow related to the initial position of the matrices. And what is interesting that does for any T we have the same expression, and therefore is somehow just a differential operator defined by the initial value T acting on any tangent vector to the Stiefel manifold, and then it can be written shorter, and this is the solution. I'm cheating here. I'm cheating a lot because it's very difficult to solve this matrix valued equation and in this, even using computers and so on, but the solution is exact. And this is not coming as a solution of that equation. We just knew that this exists and how it's look like, how it should look like, because this is solution is just solution of is just a geodesic on the Stiefel manifold. And now putting this in the situation when the Stiefel manifold is, okay, do not scare. Stiefel manifold is Riemannian, we used Riemannian submersion. So once again, we have a group and we have the projection to the group factorized by the isotropy subgroup that is diffeomorphic to the Stiefel manifold. And this was Riemannian submersion. So this situation is well known for the Lie groups. And since the metric here was bi-invariant, and this is Riemannian submersion, then the Riemannian geodesic at that level is the projection of so-called sub-Riemannian geodesic on the group G. Okay, I was avoiding this word sub-Riemannian manifold and so on, but probably I have to explain now that what is sub-Riemannian geodesic and what is sub-Riemannian manifold. The sub-Riemannian manifold is the manifold that in our case is just the group G with some distinguished sub-bundle. Okay, there are slightly different definitions, but in our case it's just a sub-bundle of the tangent bundle that was our horizontal distribution that we constructed as the orthogonal complement to the kernel of differential of that projection, and then some metric defined, okay, the scalar, metric defined on the distribution. In our case, it was a left translation of that alpha metric, yes, of alpha metric. Okay, for us is alpha metric. So this triple is called sub-Riemannian manifold. Now, any 2 points in this manifold can be connected by a curve such that at each point it's tangent to the vector that lives in this horizontal distribution. It's not obvious that you can do this, but it's possible to do if it is bracket generating, in a sense that the Lie hull of sections of that distribution generate all the tangent space at each point. And that was exactly, that is possible because the condition that, okay, K is inside of, I'm not very good to write in a Gothic, that condition that I told once, talking about that the vertical space have to be inside of the commutators is exactly, says you that any commutator from the horizontal distribution give us something in vertical, and they span all the space. Now, about the sub-Riemannian geodesic. Now we know that we can connect any 2 points by the curve that is tangent to that distribution. It's okay, but now we need to find the geodesic. In what sense? And here, there is no Levi-Civita connection. There are a lot of connections, but there is no preferred one, especially, and whatever connection you choose, such that the such that it's preserved this distribution, it cannot be torsion-free, because torsion-free, it's a contradiction to that one, to the contradiction. So there is no preferred connection, and therefore there is no way to write the geodesic equation in the sense of connections. Then the people going to the doing 2 things. First of all, they either they define the geodesic as a local minimizer of the distance function, but the distance function is produced as in the Riemannian case, infimum of all lengths of the curves connecting 2 points. But here, the curves have to be a special one, tangent to the distribution. Now we know that this infimum is not infinity because the set is not empty. Any 2 points can be connected. This is one way to define the sub-Riemannian geodesic. Another way is use the Pontryagin maximum principle or control theory, optimal control theory, where you define your Hamiltonian related to that metric, and you find the flow on the cotangent bundle, to that G on the cotangent bundle, but that metric, cometric, you can define, it will be degenerate due to the fact that our metric is not defined on the vectors, on the vertical space. So in the dual picture, we will get the cometric defined on the cotangent bundle to that G. The metric will be, cometric will be degenerate, but anyway, you define the flow, you define the Hamiltonian depending on that cometric, and then you have a flow on the cotangent bundle, and then you project to the manifold. But in this case, there are again not, the life is not so easy. This is some of them good ones, and they mimic the Riemannian metrics, Riemannian geodesics on the sub-Riemannian manifold, and they called normal geodesics. But there are some other cases, abnormal, that does not depend on exactly on metric, but they describe the property of the distribution. That fact was known in optimal control theory since 30s of the past century, so it's not a new feature. But anyway, so here, when we talk about this, we think about the sub-Riemannian geodesics in this Hamiltonian way, and these sub-Riemannian geodesics, they are normal one. So all in all, so in order to write the sub-Riemannian geodesic, since here we look on that sub-Riemannian manifold. Group, left invariant distribution, alpha metric, restriction to the distribution, alpha metric from the Lie algebra. Yes, and then this is the formula. And this is the formula for any sub-Riemannian geodesic. What is written here? UP, UT is just initial vector written as a projection to the initial, to the P that is horizontal to the T part. So this is just initial vector. This is just initial vector. And what is written here, this is just a group exponential. And since the metric is bi-invariant, according to the Milnor result, this group geodesic will be exactly Riemannian geodesic, or even pseudo-Riemannian geodesic. So it's just a Riemannian geodesic here. Okay, G0 is the starting point. But then, in order to get sub-Riemannian, in order to get something that is tangent to the H, you correct it by this exponential, again, group exponential with minus TUK. In a sense, for each T, you kill this component, and you get something that is tangent to the horizontal. And this is the formula that was known for the group for the long time. Recently, it was generalized for the principal bundles, absolutely the same formula. The only thing that here we have just Riemannian geodesic, but this guy is still coming from the vertical part, and on the principal bundle, it's still related to the group, except the principal bundle. Yes, and then direct calculation show you that that formula and the formula written in the matrix way, it is exactly the formula that solve this variational equation that is here. Okay, so I told you that I'm cheating. I'm cheating, and this is now the truth. But anyway, yes, a couple of last words before I finish, and everyone is hungry. So yes, this is like summarizing. The projection of sub-Riemannian geodesic onto the Stiefel manifold is a Riemannian geodesic, as I told. So we found sub-Riemannian geodesic at this level, but since this H is isomorphic and isometric to the tangent space of the Stiefel, then the projection of this guy here will be something that is related to the Riemannian geodesics, but the following. So any sub-Riemannian geodesic projection is the curve of constant geodesic curvature. Okay, let me go here. So you see, there is this vertical component, but it doesn't matter. Whatever curve you write like this one, you project downstairs and you get a curve of a constant geodesic curvature, where the geodesic curvature is calculated as the norm of this guy, of course, with respect of alpha metric. But if this vector, initial vector in the t direction is 0, then the projection will be just a Riemannian metric. So that's what is written here. So this is the geodesic curvature, the norm of the initial vector, vertical part of the initial vector. Yes, and in this case, for any x and any u, it was, for any u in the Lie algebra, this kind of the writing give us the curve of constant geodesic curvature. So this is a general form how to find the curve of constant geodesic curvature on the Stiefel manifolds, and this is just a consequence of that result. And yeah, this is almost last slide. There are two particular cases: when the Stiefel manifold is the sphere, and when the Stiefel manifold is a group. And so this is two cases. And in this case, so when it is the n-1 sphere, then actually, if we calculate the alpha metric, then you see that this does not depend on alpha. It's actually, for any alpha, it induces the same classical metric on the sphere. But on the group, if you calculate this on the group, yes, then we get just the killing form on the V group up to the multiple, and this multiple related to our parameter by by this 1 over alpha plus 1. So this matrix is also related with the classical one in this case. Yeah. So all the examples that I mentioned here They appeared in the literature, and they appeared in the literature because people were interested on the Riemannian positive definite metric on the Stiefel manifold. Of course, you can produce non-negative or non-positive definite, but non-degenerate metric if alpha is not equal to 1, minus 1. But okay, there are no applications, but people can work about it. Any formulas are work here. Yes, and this is the essentially the content of these 3 papers that were published rather recently. Yes, and that's all. Thank you. Yes, so Fatima Silva Leite, she's retired now, but for the long time she was working in the University of Coimbra University and in the Institute of Robototechnic that has a long collaboration with them, and they are interested in the calculations in the Stiefel manifolds a lot. Yes, and therefore it was several projects that Fatima was doing with them was request from the Robotic Institute. And therefore, yeah. And Knut, he was working in Australia for 5 years in the engineering department, and also, and that people they do not know what is Stiefel manifold. They do not want to hear about Stiefel or Grassmann manifold. They want to calculate matrices. So if you write something for them in matrices, they are happy. But if you write about Stiefel manifold, and they do not want to work with arbitrary point x, they need to have a formula. Give me the formula, then and so on. That's it. Yes. Mm-hmm. 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 Yeah. So they yes, but that geodesic can be written in this long line, just using initial point and the initial tangent vector. Yes. Yeah, okay, great. I will send you. Yes. Mhm. You know, this is a very difficult question. One thing to write geodesic that start from the point with the given direction. This is more or less it's possible to solve and so on. But if you have a boundary value problem, you have 2 points and you want to join it with geodesic, it became a headache. Actually, yes, and this is a general philosophy, not only on the Stiefel or Grassmann manifold or whatever. In general, it's difficult. But I know that one of the PhD students of Knut Hueper, he was working on this problem. And when the people were trying to mimic this Castasio algorithm, construction of the polynomial spline on the Stiefel manifold, they were trying to connect 2 points, exactly what you, with some geodesic that in Stiefel. And they didn't know how to do this. And instead of that, they considered the curves of constant geodesic curvature, prescribed geodesic curvature. And they could connect it by using this kind of very rare distribution and so on. They didn't call it like this one, but it is inside of this picture. So in general, it's difficult. But now there are some Recently I know this. I read this thesis, and thesis was very interesting in that. In Grassmann, yes. It's symmetric, and the idea was, but since the Grassmann is also can be thought as a principal bundle, as the base space of the principal bundle, where the Stiefel is the whole space, there was an expectation that somehow people can relate this problem connecting 2 points on the Grassmann and lift it to the Stiefel. There are some particular cases with precise solutions, but in general, it's headache, but there are some progress in that direction. Yeah, that's it. Thank you.